Welcome back once again to a tutorial on the Bjt working mechanism. Okay, so that's exactly what we're going to discuss right here in this tutorial. Okay, so fine. So in order to understand the process of working of a Bjt, it's quite necessary to refer to a diagram first. Okay, there you go. There's our diagram, and let's just tell you that whenever we have a BJT, we've just taken a PNP type BJT for your ease of understanding the process of the working mechanism of this device. Okay, so whenever we just keep or rather take a BJT that's not connected to any sort of voltage sources, all right, then of course, as you'll know that across a PN junction, as you'll have seen in the case of the diodes over there would exist a difference of energy levels across the junctions as such. So now we can see over here that if we just take this to be the emitter terminal over here, so correspondingly this with the base, and here's the collector. Okay, and now we can see that there are two junctions in this device. The one between that of the emitter and the base, as you'll know, is known as the emitter junction, and the one between that of the base and the collector is known as the collector junction in general, of course. So whenever we just take a PNP type BJT, as you can see in this figure over here, so you'll know that in case of a BJT not connected to any sort of voltage sources, there would be some sort of barriers, or rather depletion regions that'll basically form between that of the emitter junctions, okay, across that of the emitter junction, as you can see over here. And of course another depletion region would be formed across that of the collector junction, as you can see over here. So these lines, that the dotted lines over here in white, they represent the width of the depletion regions formed across that of the emitter and the collector junction. So I'll just label them over here. So there you go. So this would be obviously the width of the emitter, the depletion region that would occur across that of the emitter junction. Okay, and on the other hand, this one would, the other one would obviously represent the depletion region that would obviously be formed across that of the collector junction, as you can see in this figure. Okay, so this particular phenomena, or rather this particular set of events will exist whenever a BJT is not connected to any sort of voltage sources. Now if we just manage to connect voltage sources, then what would happen? Let's just check it out. Well, now you can obviously see the difference that it makes upon connecting the voltage sources. Now you can see that we have obviously forward biased the emitter base junction, that's the emitter junction over here, by connecting this voltage source V1 across that of the emitter and the base terminals. And I can see that the width of the depletion region existing across that of the emitter junction is significantly decreased. Okay, and by connecting this voltage source V2 that reverse biases the collector base junction, and this way we just increased the amount of reverse bias across that of the collector junction as such. And now due to this sort of activity, what happened over here is that the collector collector junction that has a sort of depletion region existing across it, it just widens a little bit more. So now we can understand that as you'll have seen in the case of PN junction diodes, you can see if you just compare them, the concepts that is, and then you can see that upon reverse biasing a particular junction, the amount of depletion region width will obviously increase. So that is exactly what would what we would obviously see in case of a BJT connected to forward and reverse bias voltages across that of the emitter and the collector junctions respectively. Okay, so that will obviously lead to a difference in the energy levels. Okay, so if you just refer to the energy diagrams, then as the diagram on our right shows that this is the condition of the energy levels. As you can see on the top, we have the light blue line representing the the conduction band, and the lower pink line represents the valence band, and the middle, this white dotted line represents our Fermi level. So this particular diagram over here represents the energy levels of a BJT where the voltage sources are not connected. Don't just confuse it with the energy level diagram for the diagram on the right, I mean on the left over here. Okay, so this represents a condition where no voltage sources are connected across a BJT, I mean across a PNP type of BJT. But as soon as you do this, as you can see in the diagram on the left over here, I mean as soon as you can just connect voltage sources across that of a PNP type BJT, this energy level diagram would change to, obviously, well, it'll look like something as you can see in this diagram on the right. Okay, so now you can see over here that since we've just forward biased this emitter junction over here, so you can see that, well, there's a comparatively shorter gap, or rather shorter gap of energy levels between that of the corresponding levels in the emitter and the base region. So I'll just name them over here. Here's the emitter region, this is the base, and here's the collector. Okay, so you can see that, well, there's obviously a closer gap between the energy levels in the emitter and the base region, and there's a comparatively greater gap in the energy levels present in the collector and the base region of a PNP type BJT. Okay, so under this scenario, as you can see over here, if we just care to pull the page down a bit, so under this scenario that we can see over here, it's quite obvious that with the emitter junction being forward biased, it's quite natural that the current from the emitter, which is of course highly doped, will obviously tend to flow towards that of the base. So we'll have possibly an emitter current due to the majority carriers, that is the holes over here. Okay, so we'll just call it IEP, as you'll have seen in the current components of the BJT. And we'll also have another current component due to that of the electrons that will cross over from the base into that of the emitter section. It'll look something like this. Okay, now we can call this one as IEN. Okay, but there is a small mistake. The arrow mark would just be reversed since we're just talking about the current components. Okay, so here we'd have the current component under the electron that just flows from the base into that of the emitter section. But over here, since the electrons move in a direction opposite to that of the conventional current's direction, we'll just take it in a reverse way. That's the direction of the conventional current. Okay, so now what I'm basically trying to say over here is that now due to the base being lightly doped, okay, the current, I mean the emitter current component due to this electrons, as you can see right over here, the blue line, okay, it'll be comparatively much less than that of the emitter current component due to the holes. So we can just say that IEP is obviously much greater than that of IEN. So we can obviously, if we just talk about the emitter current, it'll obviously imply that of the holes, I mean the whole component of the emitter current. Okay, so now what basically happens over here is that under this sort of bias voltage connected at the emitter, I mean across that of the emitter and the collector junctions, the emitter current would obviously flow from that of the emitter section, and then finally it would enter into the base. Okay, let's just change the colors. Okay, that's better. So it'll obviously enter into the base through this forward biased emitter junction over here. And now whenever the holes present in the emitter current component due to the holes over here, since they are the majority carriers, whenever these holes reach the base section, as it is N-type, as you can see over here, so over there the holes become minority current carriers. Okay, so in that way it sets up a concentration gradient across that of the base terminals. Okay, the concentration gradient profile is exactly as shown by this diagram over here. So you can see that near that of the emitter junction on the base, I mean across that of the in the base section of a PNP type BJT, we can see that the current component due to the holes right over here, it just increases exponentially near that of the emitter junction. So over here, right across, if I take the white color, so right across this part of the base, the emitter current component due to the holes would obviously be quite high, and it'll gradually decrease. Okay, it'll gradually decrease as we would move on towards that of the collector junction. Now the holes reaching the base and those that present in the base section of the BJT would obviously be attracted by this negative charge given by that of this reverse bias voltage V2, as you can see over here, connected due to this voltage source V2. Okay, so it's quite probable that most of the holes will be just attracted into the collector section as the remnants of the emitter current, if I just call it IC1, as you've seen in the previous tutorial, due to the whole current component, while the rest of the emitter holes would just recombine with the electrons present in the base and would constitute the recombination current. Okay, so now what happens to these the current component that reaches the collector section? It just moves out of the collector terminal as the collector current. So what we can see over here, that since the collector now the collector current over here is obviously not equal to that of the emitter current due to the holes that you can see over here. So we can just say that the emitter current, okay, we can say that the emitter current due to the hole component is obviously approximately equals to that of IC1, that's the remnant of the collector current due to the whole component coming from the emitter section. Okay, so they're approximately equal to each other, and now from this particular theory we can obviously say that the emitter current, which was obviously supposed to reach the collector terminal, reaches there uncompromised in magnitude. Okay, if we just manage to neglect the base current part, since it's obviously quite less compared to the amount of the or the magnitude of the emitter current. So if we just take it this way, that the current coming from the emitter section reaches the collector section uncompromised in magnitude and enters into a region of higher resistance, as you can see, since the collector section has lesser doping than that of the emitter section, and of course due to this higher width of this reverse biased collector junction, the resistance over here, across that of the depletion region in the collector junction, is quite high than that across that of the emitter junction, which is of course forward biased. So if we just take the emitter junction resistance to be if we just take the emitter junction resistance, JE resistance, to be about, let's say, if we just take it equals to small r, then, and the collector junction resistance, okay, if we just take that equals to capital R, then obviously capital R being greater than greater than that of the small r over here, it's quite natural that the emitter current enters compromised in magnitude from a region of lower resistance input to that of a higher resistance output. So it's quite natural that there would be a power gain provided by the transistor. So here, if we just try and find out the power, so the power in the at the input is obviously given by the emitter current IEP multiplied, its square multiplied with this emitter junction resistance, that is R. Okay, and if we just take the collector current over here, which is approximately equals to that of the emitter current component to the holes, okay, then in that case, if we just take it this way, that IC1P that square multiplied with this resistance at the collector junction, then obviously we'll have two power quantities. Okay, so this will be the power across that of the emitter junction, okay, and here we'll have the power across that of the collector junction. Okay, so now from this we can obviously tally that since this resistance is obviously greater than that of the smaller resistance R that across the emitter junction, and of course the IEP and IC1P being almost approximately being equal in magnitude, we can obviously say that the power dissipated at the collector junction is obviously greater than the power dissipated in the emitter junction. Now this obviously implies that the transistor's output power is more than its input power, which means that there is a power gain. So we can get a concept of power gain from this particular deduction over here. So we can see that due to this current entering into a higher resistance region from that of a smaller resistance region, that's where the transistor gets its name, as we can see a phenomena of transfer of resistance. We can see a phenomena of, well, transfer of resistance. So where the resistance value obviously changes. Okay, so now due to this particular phenomena, the BJT is obviously known as a BJT. I mean, sorry, that was just a joke over here. So that's why the transistor, that's what this particular device is known as, a transistor, which gets its name from transfer of resistance. Okay, and finally, if we just manage to just keep this particular voltage source, that's V2, connected across the collector and the base terminals, as a variable voltage source, then by increasing its value, we'll obviously find that the base width will obviously change. Okay, so let's just for example, let's just take V2, let's just put numerical quantities over here so that it's easier for you all to understand. I'll just rub it out. Okay, so let's just consider that, well, V2 is kept at, let's say, 5 volts for now, and due to this we have a base width across that of the we have a base width of, let's say, W1. Okay, or rather this depletion region width over here is, let's say, taken as W1. Okay, sorry, there one is not visible. Okay, that's better. So now if we just increase this to, let's say, how much? Let's say 10 volts, we'll be seeing that the width across, the width of the depletion region would obviously, well, increase from the previous value to slightly more than the previous value. So now we shall call this, well, W2. So we can see over here that, well, W2 is obviously greater than that of the first base width, that first depletion region with across that of the collector junction, W1. Okay, and now if we just go on increasing this thing to about, let's say, 15 volts, as you can see over here, well, now we can see that, well, the width has changed. The width of the depletion region across the collector junction has now changed to W3, as you can see over here, where W3 is obviously much greater than that of W2 and hence W1. So now we can just come to a conclusion over here that by varying the voltage, the reverse bias voltage source, that's V2, connected across the collector base terminals, or rather across the collector junction as such, we can obviously vary the width of the depletion region, and that is quite natural. But this leads to a phenomena. We can see over here that due to this phenomena, the base width, okay, that I just demarcate over here with red, the base width obviously decreases gradually. We can see that the base width was somewhere over here in the first case, okay, and then it decreased to somewhere over here, and now it just came down to something right over here. Okay, so we can see that we can just, due to the collector section having much more doping than that of the base region, which is obviously lightly doped, it is quite natural that on increasing the reverse bias across the collector junction, it is the base width that will be obviously compromised in order to increase the width of the depletion region existing across that of the collector junction. Okay, so now decreasing the base width obviously would result in higher, or rather steeper, concentration gradients, as you can see with this white line across that of the base region. Well, you can see that there is comparatively steeper concentration gradient in the base region, but it'll obviously lead to shrinkage of the base very much. That'll of course reduce recombination to an extent, and this is due to the fact that and that's the reason why the base is generally kept narrow, so that the emitter current that it reaches the collector doesn't undergo much of a recombination, and its amount remains undiminished and uncompromised in magnitude. Okay, so now this reduction in base width with the help of the reverse bias voltage is referred to as the early effect. Okay, we shall just call this one as the early effect. Okay, so we'll just keep this in mind, and it'll be quite useful in order to understand the output curves of the BJT. So with that discussed over here, we just come to the end of this tutorial video. Hope you've enjoyed, and see you next in our forthcoming tutorial. So till then, it's just thank you for now and goodbye.